Welcome to solverfy.
There are two forms of the Heisenberg uncertainty principle involving different wave phenomena for matter waves or photon waves. It really is all the same. But the one that is most known to people is that the uncertainty in momentum times the uncertainty in position of a particle is greater than or equal to h bar over 2. So that one is famous because it says you cannot know the position and motion accurately simultaneously for a matter wave. The other form looks like an uncertainty in time and an uncertainty in energy, and it has the same form. It's greater than or equal to h bar over 2, where h bar is Planck's constant over 2 pi. So this quantity is h over 4 pi at minimum. And the interpretation here is that if you start to look at the spectrum of a natural source of radiation, it will typically, if there are discrete energy levels, it will create spectral lines in its intensity versus wavelength spectrum. Those lines do not have infinitely narrow width. They have a certain width associated with them. And because there's an uncertainty in wavelength, that uncertainty in wavelength is associated with, we won't get into this too much, uncertainty in the energy that the particle had before it made the transition. And so the delta T then is associated with the lifetime of the state. Lifetime of the, for example, electron in this energy level. And so we can see that the shorter the lifetime there is, the smaller the delta T, the larger this so-called natural line width will be. That's what it's called. Natural line width is the delta lambda. And it's coming about because of the uncertainty principle. So if you've always wondered how they know certain states decay after X amount of seconds, this is usually how they do it. Now, in this question, they kind of go the opposite way. We're told that the lifetime of the state is 5.2 times 10 to the minus 3 seconds. And we want to find the uncertainty in the energy level. And notice that this is not a strict equality, so we will actually be calculating the minimum delta E. There are versions of the Heisenberg principle that says, bump it up to h bar, but we'll find the minimum. Uncertainty then occurs with the equality, and it's h bar, which is h over 2 pi, divided by 2, 4 pi. Here I'm going to use, so we have a better feeling for the answer, I'm going to use the version of Planck's constant that's in eV seconds. Okay, so we can put that known fundamental constant in. Whoops. And we can divide by 4 pi and the lifetime of the particle in this particularly long-lived state. And what we wind up with is quite a small number. Let me check the number. And we're getting about 6.3 times 10 to the minus 14 EVs. And I will point out that this is a very small number. Typical energies that come out of atoms, like the hydrogen atom, are usually of the order of a few EVs if they create visible light. So the possibility of seeing this show up in the line width seems fairly minuscule. And like I said, the number that they give for the lifetime seems a little bit opposite of what is done experimentally, where usually the line width is an indicator of the lifetime of that state.